In the previous video, we already learned one contribution of mathematics in political science, which is voting. Now, in this video, we're going to learn another contribution of mathematics to political science, which is apportionment. Consider that what you're going to learn in this video is not limited to the assignment of number of seats in the Congress, as these methods may also be applied in assigning the number of firemen in different districts, number of teachers in a certain town, and number of healthcare workers or nurses in different cities, and a lot more. Before we start, we have some definitions to consider, such as states, which are parties having stake in the apportionment. This may also be cities, regions, towns, or municipalities. Seats, which are the number of indivisible objects which are assigned in different states. This may also be the number of firemen, number of teachers, or the number of nurses assigned to different cities. Population, a positive integer n which refers to the number of citizens or residents in a locale. And this will be the basis of the seats to the states. In its simplest definition, apportionment is the act of dividing people among places. In this video, we're going to learn 6 different methods of apportionment, which are the Hamilton method, Jefferson's method, Adams method, Webster's method, Hill-Huntington's method, and the Lowndes method. Let's begin with the Hamilton method, which is named after Alexander Hamilton, who proposed this method in 1792. This is the first method used to apportion the seats in the U.S. Congress. This method was adopted to apportion the U.S. House of Representatives every 10 years between 1852 to 1900. The steps in the Hamilton's method are as follows. First is compute for the standard divisor D, which is the quotient when the total population is divided by the number of seats or representatives. Next is to compute for the standard quota, which is the quotient of the state's population when divided by the standard divisor D. Then get the whole number part of the standard quota, or in other words, round it down and call it as the lower quota. Next is add all the lower quota and check if it is equal to the total number of seats or representatives. If it is already equal to the number of seats or representatives, then we're done with the apportionment. But if not, the remaining number of seats or representatives will be assigned to the state whose decimal value of the standard quota are the highest. That is why the Hamilton's method is also called as the largest remainder method. For example, using the 2015 population of the Philippines per region, and we want to allocate the 250 members of the House of Representatives, using the Hamilton's method, first is we get the standard divisor, which is the quotient of the total population divided by the number of representatives, and that is 403,925.75. Next is we get the standard quota of each state, called as regions, by dividing the population of each region by the standard divisor. Next is cut off the decimal parts of the standard quota, or round it down. Or in other words, we simply get the whole number part of the standard quota, which will be called as the lower quota. Next is we add all the lower quota, and since the sum of the lower quota is just 240, this indicates that 10 representatives have no designation yet. So we apply the largest remainder rule, in which the remaining representatives will be assigned to the regions with the highest decimal parts of the standard quota. Since 10 representatives have no assignment yet, the 10 regions with the highest decimal value in their standard quota will receive 1 extra seat, in which in this case we have 0.992 from Region 8 as the highest decimal value, followed by 0.986 from Region 9, 0.958 from Region 7, 0.928 from NIR, 0.880 from the NCR, 0.773 from Region 3, 0.687 from Region 4A, 0.609 from Region 10, 0.545 from Region 2, and 0.443 from Region 1. They will all receive 1 extra seat, so our sum of allocation is now 250. Using another example wherein suppose we are asked to assign 100 doctors to different parts of Metro Manila during New Year's Eve due to firecracker reported injuries that may happen. Allocations will depend on the number of reported injuries of the previous years, in which the table on the right we can see the report of the World Health Organization of the reported firecracker injuries from 2010 to 2014. Using the Hamilton's method to determine how many doctors have to be assigned at the different parts of Metro Manila, the first thing that we have to do is to divide the total, which is 2,810, divided by 100 doctors, and that is the standard divisor, which is 28.10. Next, we're going to divide each number of reported injuries with the divisor, which is 28.10. And we're going to have these values for the standard quota. Next is we're going to remove all the decimal values of the standard quota, or in other words, we're going to round down the values. And that gives us the lower quota with values 19, 18, 10, 10, 9, 8, 8, 7, and 7. However, the total here gives us 96 doctors, which lacks 4 more doctors. So to assign the 4 remaining doctors, all we have to do is to take a look at the decimal values of the standard quota. Since we need to assign 4 more doctors to complete the 100 doctors, all we have to do is to get the top 4 highest decimal values in the standard quota, which are Quezon City's 0.967972, Pateros 0.758007, Pasig's 0.718861, and Mandaluyong's 0.50178. And since these are the cities with the top 4 highest decimals, we're going to assign 1 additional doctors to these cities. And that leaves us with 20 doctors to be assigned in Mandaluyong, still 18 for Manila, still 10 for Marikina, 10 for Las Piñas, and 9 for Navotas. Then 9 for Quezon City, 9 for Pasig, 8 for Pateros, and still 7 for Valenzuela, having a total of 100 doctors. Now, the problem with this method is that increasing the number of seats may cause a party to lose a seat, and that is called as the Alabama paradox, which happened in the state of Alabama in 1880. To illustrate the Alabama paradox, in this example, as we can see, there are 3 states, A, B, and C, with 10 seats. A and B get 4 seats, while C gets 2. However, when the number of seats are increased to 11 with the same population, although the share of A and B increased from 4 to 5, the share of C decreased from 2 to 1. Next is the Jefferson's method, which was an idea of Thomas Jefferson. This method was adopted by the U.S. Congress in 1791 to 1842. In this method, the first 3 steps are the same as the Hamilton's method, wherein step number 1 is to find the standard divisor, which is the quotient of the total population divided by the number of representatives. The second step is to get the standard quota of each state or region, which is the quotient of the population of each state or region divided by the standard divisor. Third is to cut off the decimal value of the standard quota to get the lower quota. However, in step number 4, instead of finding the highest decimal values, in the Jefferson's method, we have to reduce the standard divisor, called as the modified divisor, until the lower quota's sum is equal to the number of representatives. So in the previous example, we just have to reduce the standard divisor until the lower quota's sum is equal to 250. Now, for simplicity, let's have another example wherein a House of Representatives of a certain country needs 41 new members to divide among the 3 states A, B, and C. The population data of the 3 states are as follows. Using the Jefferson's method, how we're going to allocate these 41 new members? The first thing that we have to do is to compute for the standard divisor, which is the population 897,934 divided by the 41 members, and that gives us 21,900.83. And computing for the standard quota of each state, simply we're going to divide each population by 21,900.83, and we're going to have these values. Then we have to cut off all the decimal parts of the quotas, which gives us 7, 24, and 9, and adding the remaining whole numbers, we have 40. Now, since this total lacks 1 member, we have to assign 1 member to either state A, B, or C. And how do we do that? We just have to reduce the standard divisor, which is 21,900.83, until the sum of the lower quota becomes 41. And by trial and error, I came up with this modified divisor, which is 21,000. And dividing each population by 21,000, we're going to have this standard quota. Cutting off the decimal values, we're going to have 7, 25, and 9, which leads to a sum of 41, which completes the 41 new members to be assigned in different states. Now, using the previous example wherein we're going to determine how many doctors have to be assigned at different parts of Metro Manila, we came up with the standard divisor using the Hamilton's method of 28.10. And since using the standard divisor of 28.10 will lead us to the sum of lower quota, which is just 96, we have to reduce the standard divisor. And by trial and error, I came up with the standard divisor, which is 27. And dividing each number of reported injuries by 27, we're going to have the standard quota of these values. And cutting off its decimal values, we're going to have 20, 18, 10, 10, 9, 9, 9, 8, and 7, which leads a total of 100, which now completes the total number of doctors to be assigned in different cities. Next, we have the Adams method, which is named after Quincy Adams in 1822. This method is the exact opposite of the Jefferson's method, in which after getting the standard divisor, instead of rounding down the standard quota, we round it up and get the upper quota. And if the sum of the upper quotas is higher than the total number of representatives, we get the modified divisor by increasing the standard divisor until the sum of the upper quotas is equal to the total number of representatives. Now, using the same example, wherein the House of Representatives of a certain country needs 41 new members to divide among the three states A, B, and C. Having a population of 897,934, we're going to use the Adams method to allocate the 41 new members. In which, similarly, we're going to compute for the standard divisor, which is just the population divided by the number of members, in which we're going to have 21,900.83. And dividing each population by the standard divisor 21,900.83, we're going to get the standard quota, which contains these values. Next is we're going to round up the standard quota to get the upper quota, which indicates that we simply have to add 1 with the whole number in the standard quota. So in other words, the upper quota will just be 8, 25, and 10, which gives us 43 members, which exceeds 41 new members. Now, to reduce this total of the upper quota, all we have to do is to increase the standard divisor, in which by trial and error, I came up with the modified divisor, which is 23,000. And dividing each population by 23,000, I came up with the standard quota having these values. And rounding up these values, meaning we're just going to add 1 with the whole numbers of the standard quota, gives us 8, 24, and 9, which comes up with a total of 41, which completes the new members of the House of Representatives. Now, applying the Adams method in the same example wherein we're going to assign the different doctors to different parts of Metro Manila, and using the Hamilton's method, we came up with 28.10 as the standard divisor. And using the Adams method, we just simply have to increase the standard divisor. And by trial and error, I came up with the divisor, which is 28.99. In which when we divide the number of reported injuries by 28.99, we're going to have the standard quota with these values. And rounding them up, we're going to have 19, 18, 11, 10, 10, 9, 9, 8, and 7. However, the total exceeds by 1 since we only have to assign 100 doctors. Now, to decrease this total of the upper quota, we just have to increase the divisor. However, when I use 29.0, which is just 0.01 higher than the previous divisor, I came up with the standard quota, and rounding them up, we're going to have this upper quota values, which led to a sum of 99. Which indicates that Adams' method failed to assign the 100 doctors no matter what the divisor is. Next, we have the Webster's method, which was proposed by Daniel Webster, which was used in the U.S. Congress from 1842 to 1852, 1911, and 1931. In this method, we still have to get the standard divisor first and divide each state population by the standard divisor to get the standard quota. But unlike in the Hamilton's method and the Jefferson's method, where we round down the standard quota to get the lower quota, and unlike in the Adams method, where we round up the standard quota to get the upper quota, in Webster's method, we round off the standard quota, then get its sum. But if the sum is greater than the total number of representatives, we increase the standard divisor. If the sum is less than the total number of representatives, we decrease the standard divisor until we get the total number of representatives. Using the same example, wherein the House of Representatives of a certain country needs 41 new members to divide among the three states A, B, and C, in which their population is 897,934. And using the Webster's method, similarly, we have to compute for the standard divisor, which is the total population divided by the number of seats. And we're going to have 21,900.83. And dividing each population by 21,900.83, we're going to have the standard quota, which are these values. And since the Webster's method, simply round off the standard quota to get the rounded quota, then 7.4 when rounded off is 7, 24.587 is 25, and 9.002 is 9. And that gives us a total rounded quota of 41, which is enough to allocate the 41 new members. And using the previous example wherein we're going to assign the different doctors in different parts of Metro Manila, using the Hamilton's method, we came up with the standard divisor of 28.10, which is just 2,810 divided by the 100 doctors. And dividing the number of reported injuries by 28.10, we're going to have these values of the standard quota. Then all we have to do is to round off the standard quota. And rounding off 19.5, we're going to have 20, 18.07 is 18, 10.32 is 10, and similarly 7.188 is just 7, which gives us a total rounded quota of 100, which is already the total number of doctors. The Hill-Huntington's method is the idea of Edward Huntington and his classmate Joseph Hill. And this method is the one currently being used to apportion the seats in the U.S. House of Representatives since 1941. In this method, we still have to start with the standard divisor followed by the standard quota. And to decide whether the standard quota will be rounded down or rounded up, we have to compare it with the geometric mean, which is the square root of n plus 1, where n is the lower quota. If the standard quota is higher than the geometric mean, we round up the standard quota. But if the standard quota is less than the geometric mean, we round down the standard quota. Then we get the sum of the rounded quotas. If it is less than the total number of representatives, we decrease the standard divisor. And if the sum is more than the total number of representatives, we increase the standard divisor until the total number of representatives is achieved. Using the previous example, wherein the House of Representatives of a certain country needs 41 new members to divide among the 3 states A, B, and C, in which their population is 897,934. Using the Hill-Huntington's method, similarly, we're going to find the standard divisor, which is 21,900.83, and dividing each population by the standard divisor, we're going to have the standard quota, which are these values. Next is we just have to round down the standard quota to get the lower quota. So rounding down 7.4, we have 7, 24.587, we have 24, and 9.002, we have 9. Now, these values of the lower quota will be the value of n in the square root of n plus 1, which is also called as the geometric mean. So, computing for the geometric mean, for state A, we're going to have the square root of 7 times 7 plus 1. Computing for the geometric mean of state B, we're going to have the square root of 24 times 24 plus 1. And computing for the geometric mean of state C, that is square root of 9 times 9 plus 1. And computing for these values, we're going to have 7.483, 24.495, and 9.49. Now, to decide whether the standard quota will be rounded down or rounded up, we just simply have to compare it with the geometric mean. In which, if the standard quota is less than the geometric mean, we have to round this down. And if the standard quota is higher than the geometric mean, we have to round this up. Now, since 7.41 is less than 7.483, we have to round this down, and that is 7. On the other hand, since 24.587 is higher than 24.495, we have to round this up, so this becomes 25. And since 9.002 is less than 9.49, we have to round this down, so that is 9. And that gives us the allocation, which is 7, 25, and 9, which gives us a total of 41, indicating that we were able to allocate the 41 new members. And using the previous example wherein we're going to determine the number of doctors to be assigned in different parts of Metro Manila, again using the Hamilton's method, we came up with the standard divisor of 28.10. And using that standard divisor, we were able to come up with this standard quota, which when rounded down gives us these values. And using these values to compute for the geometric mean, for Mandaluyong, we're going to have the square root of 19 times 19 plus 1 as its geometric mean. For Manila, we're going to have the square root of 18 times 18 plus 1. For Marikina, we're going to have the square root of 10 times 10 plus 1 until we have the square root of 7 times 7 plus 1 for Marikina. And that gives us these values of the geometric mean. Now, to decide whether we're going to round up or round down the standard quota, all we have to do is to compare it with the geometric mean. Since the standard quota is higher than the geometric mean, we're going to round this up. On the contrary, since the standard quota is less than this geometric mean, we're going to round this down. Similarly, since the standard quota is lower than this geometric mean, we're going to round this down. Since the standard quota is higher than the geometric mean, we're going to round this up. Same rule applies in other cities, and we're going to have these allocations. And since the total initial allocations is 100, then we were able to allocate the 100 doctors to the different cities. Last, we have the Lowndes method, which is by William Lowndes. Unlike the previous methods, this method has never been used in the US Congress. In this method, still we start with the standard divisor followed by getting the standard quotas. And similar to Hamilton's and Jefferson's method, we round down the standard quota to get the lower quota. And expectedly, the sum of the lower quotas will be less or equal to the total number of representatives. Then the remaining number of representatives will be assigned to the states with the highest ratio, in which ratio is computed as the decimal value of the standard quota divided by the whole number of the standard quota. That's why the Lowndes method is also called as the largest relative fraction method. Now, using the Lowndes method to allocate 41 new members of the House of Representatives in the same example, wherein the total population is 897,934, still we have to compute for the standard divisor, in which we came up with 21,900.83. And dividing each population with that divisor, we're going to have this standard quota. Next is rounding down the standard quota to get the lower quota, so this will become 7, 24, and 9. And since the total here is 40, which lacks one new member, we have to assign one member to either state A, B, or C. And that allocation will be based on the Lowndes method, which tells us to divide the decimal part with the whole number. So 0.411 will be divided by 7, 0.587 will be divided by 24, and 0.002 will be divided by 9. And that gives us a ratio of 0.0587, 0.0245, and 0.002. Now, since the lower quota has a sum of 40, which tells us we only have to assign one new member to either state A, B, or C, and that is to be determined by the one with the highest ratio. And since the highest ratio is 0.0587, then we're going to assign extra seat for state A. So state A will have 8, state B will still have 24, and state C will still have 9. And that gives us a total of 41. Now, using the same example wherein we're going to assign 100 doctors in different parts of Metro Manila, using the Hamilton's method, we came up with this standard divisor. And dividing each number of reported injuries with the standard divisor, then we have this standard quota, in which when rounded down gives us these values of the lower quota, giving us a sum of just 96 doctors. Now, since this total of 96 doctors is 4 less than the total number of doctors, which is 100, applying the Lowndes method, we have to divide the decimal value with the whole number. And dividing the decimal value of the standard quota with its whole number value, we're going to have this ratio. And since we need 4 more doctors to be assigned in the different cities, we simply have to get the top 4 highest ratio. And those are 0.12, 0.1082, 0.0898. And since there's a tie in the 4th place, which is 0.030, we may assign the last doctor to either Marikina or Navotas, in which in this case I assigned it to Navotas. So additional seats were given to Quezon City, to Pasig, to Pateros, and to Navotas, since again they have the top 4 highest ratio. And that gives us a total of 100 doctors, which indicates that we were able to allocate the 100 doctors to the different cities. Although in this video we only limited to 6 methods of apportionment, there are still other methods of apportionment. The Dean's method, which uses the harmonic mean instead of the geometric mean. The Condorcet's method, which rounds off the standard quotas using 0.4 as the cutoff. Note that none of these methods are applied in the Congress of the Philippines since seats are already specified in the 1987 Philippine Constitution. Now, this ends our lesson in the methods of apportionment. If you happen to like this video, do not forget to click like, subscribe, and hit the bell button so that you will be updated in my upcoming videos. We would like to give special thanks to Dr. Ezra Aguilar for the content contribution to this presentation.